Okay, so let's explore the concept of difference in electric potential energy around the path, and in particular, a closed path. So we come back to our initial point. The difference in the electric potential around that path and the work W done. So we want to show that these quantities around the closed path are all zero because they're all related to each other. So let's think of a charged particle of charge Q naught. We know the electric field, and let's consider a path which is a circle of some radius. Let's make the radius R naught. Okay, so let's consider the work done around that path. So we start at some point and we come back around to that point. So the work is, by definition, the integral of the force along that path. So at every point there's the force dot dr. So in order to have an electric force, we need to have a charged particle. So we're going to place a charged particle on this path of charge, let's say Q star, and move it around the path that way, and consider the work done by the electric force. So the electric force, so both of these particles are positively charged. So we know that the electric field is pointing, here it's pointing that way, it's pointing radially away from the particle of charge Q naught, but the electric force is also pointing that way. So here is the electric force at that location, and when we move the particle over here, of course the electric force will be directly away, so is the electric field, and so on at every single point. And the magnitude of the force will be the same because we are at the same distance from the particle. So over here the force will be more or less that way, and over here it will be this way. And let's label F. And so we're integrating F dot dr along that path. So let's make some drs. So the drs are along that path. So here is a little dr, a little element of that path. It also has direction. It's an infinitesimal vector, an infinitesimal length, but it has direction, and the direction is tangent to the circle. So let's make drs at every point where we have an F. And we can easily see, we don't have to worry about coordinates to figure this out, but at every point the dot product is zero because these two vectors are at 90 degrees to each other, right? So there's 90 degrees here, here, and so on everywhere. Not the best drawing there, but it should be 90 degrees everywhere. So the dot product gives us zero. So actually this is zero at every single point, but it's true all the way around as well. So it must be true that delta U is also equal to zero because minus delta U is the work. And U is just related to the electric potential difference phi by the charge. So we divide by a charge, and of course if delta U is zero, then delta phi will also be zero. So this is a special case where the work is zero at every single point, but we can imagine doing this integral on a different path. So here is a more complicated path that looks like that. And so if we put our particle of charge Q1 at different locations, so here the force will be that way, here the force would be that way, and the magnitude is changing, so here the force is a little bit smaller because we're further away. And so we see at different places, dr is always tangent. So here you can maybe see that F dot dr is 0 because they're perpendicular to each other, but along here, that's no longer true, right? This is less than 90 degrees. The same is true here. So we have places where the contribution is not 0. But overall, if you did that calculation, you would find that the work done on a closed path, so maybe we should do this here and indicate closed path. We come all the way back around, we would get 0. That would be a complicated calculation. Let's do a calculation where we can actually evaluate this quantity at every point. So maybe we can consider the infinitely large plane uniformly charged with charge density sigma. And let's imagine a path that goes, let's see, we could, let's just use a rectangular path that looks like this. And maybe this side is L and this is, I don't know, D. And let's draw the electric field. So in this case, let's imagine there's no charged particle there. So we're actually evaluating not the work, but it's the integral of the electric field all the way around that path. So closed loop integral of E dot dr, right? This is related up to a minus sign to delta phi, electric potential difference. So let's do electric field in red. So we know the electric field is pointing above, it's directly upwards. So along the path here, it's pointing that way. And we know the magnitude. So here it's pointing that way. Here it's pointing that way with the same length. So on. Here it's pointing the same. Everywhere it's pointing the same with the same magnitude. So it's a simple calculation, but we don't get 0 at every point, right? The DRs, if we're going around this way, then the DR is pointing that way. There it's pointing that way. Here it's pointing this way. So along here, the top part, we obviously get 0 because of 90 degrees between DR and the electric field. DR is this way, so it's directly opposite the electric field here. Didn't draw my electric field very well here. It should be red. And on this side, again, we get 0 because we can see it's 90 degrees. So on the top and bottom sides, we get 0. But on this side, we get the magnitude of the electric field, which we know to be sigma over 2 epsilon naught, times the length, which is d. On this side, instead, they're opposite. So we have the cosine of pi, or 180, and that gives us a minus sign. So we get sigma over 2 epsilon naught times minus d, and of course, that adds up to 0. So the closed loop integral of the electric field is 0. Delta phi is 0, and that's related to difference in electric potential energy. That's 0, and the work, of course, is related to this by a charge. It's just a constant, so the work must also be 0.